All right, in this lecture we are going to talk about uniform circular motion and something going in a vertical circle. And we have done this uniform circular motion before with things going in a horizontal circle. This time we're going to look at things going in a vertical circle. And when things went in a horizontal circle, we talked about the sum of the forces acting in the x direction is equal to the centripetal force. Now, with vertical circles, it's not quite so simple. There are going to be times when the sum of the forces in the y direction is equal to the centripetal force, and there are going to be other times when the sum of the forces in the x. So right now let's take a look at, we've got a ball on a string being swung in a vertical circle. And the free body diagram for this ball is going to look like this. We've got mg going down, and if we're swinging this thing fast enough, there's also a tensional force in the string going down that is working with the weight to keep the ball going in a circle. If we move the ball to being at the bottom of its circular motion, then we've got still the weight going straight down, but this time the tensional force has to be going up in towards the center of the circle. And we would expect the tensional force at the bottom of the ball's motion to be greater than the tensional force at the top of the ball's motion. Because at the bottom, we have the tension counteracts the weight and it supplies some extra force that acts as the centripetal force. At the top, tension and weight work together. But in both of these cases, we are looking at the sum of the forces in the y direction is equal to our centripetal force. So the sum of the forces in y is going to be equal to mv squared over r. All right. Now, there's also a third possibility here. At the very top of the ball's arc, we could spin it at just this perfect velocity where the tension in the string is completely zero. I'd love to just pull that one tension out of there, but it's not going to let me. So that's called a critical velocity, essentially. It's the velocity, the minimum velocity that we'd have to swing this ball at so that the tension at the top was zero, and the only thing supplying the centripetal force at that point would just be the ball's weight. Okay, we can talk about roller coasters. People sitting in a seat in a roller coaster, there's this minimum speed that the roller coaster needs to have so that the people would stay in their seats even without a seatbelt. Okay? Now, other things that we can look at here, and some problems we might be forced to deal with, is vertical circles where the ball is here, where the object is here at the side of the circle. And in this case, free body diagram, we still have the weight of the ball going down, but this time the tension is going in towards the center. And the tension is going to be something in between what it was at the bottom and what it was at the top. It's at a minimum at the top, a maximum at the bottom, and it is increasing this entire way down. The tension would decrease this entire way up. All right? But for this situation over here, on the left-hand side, we would be looking at the sum of the forces in the x direction would be equal to mv squared over r. Because that tension is acting in the x direction, pointing in towards the center of the circle, the weight has nothing to do with it at this point. All right? So let's work an example problem where we deal with these vertical circles. So again, we got a ball on a string, and let's say that this is some radius r. The ball has a mass m, and it's being swung around in a circle this way with some v. All right, so the first question we're going to answer is, what is this minimum velocity that we need in order for the ball to continue going in a circle, but for the tension in the string at the top to be zero? So the free body diagram for this situation is just mg going down. That's it, no tension. So mg supplies all the centripetal force that we need. So we go back to our tried and true, the sum of the forces in the y direction is equal to the centripetal force. The sum of the forces in the y this time is just mg. I'm going to say down is positive just for fun, and that's equal to mv squared over r. So this problem is super easy to solve for. We're solving for v again. Masses cancel out, so the mass of the ball doesn't even matter. And we have gr. Take the square root of that. That's going to give us v. So this is that minimum velocity. It's maybe even worth remembering for future problems. Square root of gr will give you that minimum velocity for a vertical circle. Let's plug in some numbers here and actually get some numbers so we can solve other types of problems with this. Let's say that the radius is an easy 1 meter, and let's say that the mass is 0.5 kilograms. And that's all we need to get a number for our minimum velocity. It's the square root of g, which is 9.8, times 1. The square root of 9.8. And the square root of 9.8, throwing that into the calculator, we get 3.13 meters per second is equal to our minimum velocity to keep this thing going in a circle. All right, so not super fast. Okay, now let's say we're going to swing this sucker around with a little bit more than that minimum velocity. Let's say now that we're swinging around with a velocity of 5 meters per second. How that changes our situation here is that now we're going to have a tensional force going straight down. And we want to know what that tensional force is. And then maybe we also want to compare the tensional force to when the ball is at the bottom of its swing. We know that it's going to be larger than it was at the top. So let's find the tension at the top and the tension at the bottom. Okay, so T at the top is equal to question mark, and T at the bottom is also equal to some unknown. Let's use a little bit of a magic eraser here and set up for this problem. All right, now for this problem, let's solve for the tension at the top. We still have the sum of the forces in the y direction is equal to the centripetal force, but now we've got one more force acting at the top. We have tension and we have weight. Let's again call the downward direction positive. So that means that we've got tension at the top plus mg is equal to mv squared over r. We are solving for TT, so wow, this is super easy. We've got TT is equal to mv squared over r minus mg. And plugging in some values here, we've got 0.5 times v squared, which is 25, divided by 1, minus 0.5 times 9.8. So half of 25 is 12.5, and we're going to subtract off 4.9. Throwing that into the calculator, because I don't trust myself with these numbers, as you've seen in class, we end up with a tension of 7.6 newtons for the tension at the top. Seems relatively reasonable. Now we're going to plug in some numbers and find the tension at the bottom. We should expect a larger tensional force at the bottom. So let's go magic eraser again, and this time solve for the tension at the bottom. At the bottom, we've got this free body diagram here, so we still have the sum of the forces in the y direction. Let's go ahead and call upward our positive direction this time. So we've got TB minus mg is equal to mv squared over r. And solving for TB, we end up with mv squared over r plus mg. Plugging in numbers, 0.5 times 25 divided by 1 plus 0.5 times 9.8. And same familiar numbers, we've got 12.5, this time plus 4.9. So 16, I'm going to try and do this one in my head. How about 17.4 newtons is equal to the tension at the bottom. Tension at the top was 7.6. Tension at the bottom, 17.4. Makes sense given what we talked about conceptually. The tension at the bottom should be greater than the tension at the top. All right, let's solve one more kind of problem. Let's say this ball is on a string, right? And this string can only take a maximum tensional force of 50 newtons. How fast can we swing the ball before the string breaks? Magic eraser time. So in this problem, T max is 50 newtons. So we want to find out what is that maximum velocity that we can swing the ball at just before that string breaks. And here we use our conceptual understanding of what's happening with the motion of this ball. we know that the tension at the bottom is going to be the greatest. It's the largest tension of any place on the circle. So that's where we're going to look at our free body diagram. We still have the sum of the forces acting in the y direction is equal to the centripetal force, mv squared over r. And we still have the same situation. We're going to call up positive, down negative. So we've got TB minus mg is equal to mv squared over r. This time we know the tension at the bottom is going to be T max, 50 newtons. So let's go ahead and plug that in. T max minus mg is equal to mv squared over r. And we're looking for v this time. So let's do some algebra. We will multiply everything over here on the left by r. And we're going to divide by m. And we're going to go ahead and take the square root. And that is going to equal rv squared. So we put in some numbers down here on the bottom. We've got the radius, which was 1. T max is 50. We're going to subtract off 0.5 times 9.8. And we're going to divide the whole thing by the mass, which is 0.5. Take the square root. Throwing that into the calculator, we get... Calculator returns an answer of 9.5 meters per second. And again, in the context of this problem, makes sense. The minimum velocity was 3 point something. I don't know. It was less than 5. And we just did a problem with 5, where the tension was 17.4, and now we have a maximum velocity of 9.5, if the maximum tension in the string is 50. All right, that's it. The problems work the same if we're talking about the forces on a pilot and a jet, whether he's at the bottom of a circle or at the top of a circle. We can have all sorts of fun with roller coasters, people in their seats at the bottom, people in their seats at the top, even a car cresting the top of a hill, which I think is part of your homework tomorrow that you'll be doing. We can look at forces happening there. How fast does the car need to be going for it to catch air, like my friend Chris Fairchild did in what was that? Junior year of high school in his old Buick station wagon. It was pretty scary. All right, that's it. I'll see you tomorrow.